Ready? Yes. We start. I am group one. I am Jay Kai.
How?
I am. I am Jay Kai. Eh? Yeah, okay. Let's start. First we start the preparation. Yes. Prepare the data. As we can see, we load the data of IMBD. We can see the data type is numpy and array, and the length and the size of the x and y data is 225,000. And next, we can see the first first uh first data is a list, not array, and y the y train is the label. We can see this. Next, we set the number word is 5,000 and let get the word index, and we oh, okay, I deleted. Yeah, yeah.
You deleted some code?
I changed something, and then we print the type of index. We can see the type of index is dictionary, and the length of index wait a minute. Why is that?
Mama lie.
And the size of the uh, index is about 89,000, and we reverse it and print the uh, print the dictionary. We can see the index 0 is none, there is nothing at all, and 1 1 to 9 is the and
Makes sense, right? Makes sense.
so we set the then we uh then we set the index 0 and to 3 for this. 0 is heading, first is start of the center, second is unknown, and third is unsafe. This unsafe is not necessary. Mm. Then we decode then we can see the first example before the decode.
Yeah.
And after the decode, we can see there is UNK. That is where is the phone? This here.
Two.
Then next uh we padding we do padding. So this is post padding and this is pre padding.
Correct.
Then we can see the example after padding. This is post padding. There is 0 after the sentence end of the sentence. This
Okay.
pre-pending. This is before the starting of the sentence.
Yeah.
We can see the example before the padding. There is 218 words, and after the padding, we set it to 500 words.
Correct. Correct.
This also the prepare the post-pending and pre-pending the dataset. We can see there is and we different it for we set a threshold in 100 to separate the long sentence and short sentence. We can see they have 2,800 sentence about. There is 22,000 word. There is long sentence.
Okay.
你 okay. So I do the work of GRU. So we say about GRU first. This
Okay.
is the model of GRU.
So you have, just say there, how many hidden layers? Auto-notion, input length, max length.
Wait a minute.
Okay, so no hidden units, okay? Good.
那叫什么？
The hidden units. You can choose the hidden units in the GRU module, right?
Yeah.
Okay, go ahead.
Then we train the post pending, and we can see there is
What's your
occurrence.
accuracy? Okay.
The short sentence occurrence is this, and the long sentence occurrence is this.
Okay.
This is the graph of the model.
Okay.
Yes. We also train the repending. There is the currency and the loss. They and the graph, the center pending also.
Okay.
So we can see this model can use that is good at however what's pending that is perform well, because it is also because the
Don't
occurrence
scroll
is
so much. Don't scroll so much. Avoid. Don't scroll like a crazy person. Okay. Don't scroll back and forth. Otherwise, you get epilepsy. Go ahead.
the occurrence is above 70%. So the model can perform well in these three pending.
But you're overfitting, right? So you're overfitting.
However, we can see the short sentence occurrence is below the long sentence occurrence.
Does it make sense to you?
Yes, makes sense, because the data set is smaller.
So since the data set is smaller, what's going to happen?
There is not enough data to train it.
Very good. And are you overfitting, you think?
Fitting.
Are you overfitting?
Not fitting well. Is we not fitting well for short sentence.
Okay, go ahead.
Then we do about the noisy padding. This is three in the noisy padding, this perform not very well, because we can see the occurrence is same. This is post. This is center noisy padding. In the pre-noisy padding, they perform well.
So this is what is this? Come again. What performs well? Pre-noise padding, right?
Pre-noise. But in post-noise, they perform not well. You can see.
Why? Do you have an intuition why?
don't know. I don't know why.
Of course. No, you never know.
In the reflective padding, we can see this is the reflecting padding. Is same
Mhm.
like mirror. And in reflecting padding is also perform well.
Okay, that's good.
哦，随便啦，我包什么？因为等会给准备找。
Is there, yeah.
And next is CNN architecture.
Okay. Go ahead.
反正上学期我也是报的那么烂，它已经关了。
The data processing is the same as before,
Mhm, mhm,
except the model has been changed to CNN.
mhm, mhm.
And there is different padding,
Mhm.
all pretty same time. And trend, there is a trend model.
Let me see. Batch 64. Okay, good. Can you show me the network? Stay on the network a second. Go up. Let me see the network. Let me see the network. Go up. Yeah, stay there. Stay there. Stay there.
What?
Stay there. Don't move. Don't move.
Okay.
So you have no pooling. Conv, drop out. Go down a little bit. And then you have max pooling. Yeah, you have max pool 1D. What's the size of the pool? I want to see the network. Let me see the network. Yeah, stay there. Don't move. Don't move. Drop out 64. Max pool 1D. Okay, go ahead.
Okay. And return short and long. But I haven't visualized the result yet.
Just tell me what is the accuracy, right? Let me see the accuracy. 0.
我帮你视觉化啦，帮你视
0.83 for the. So that's the short one. CNN is 0.833. Okay, go ahead.
Yes.
And the long is
帮你做了，没错。
0.83. And the test long, what is the test long? Test long accuracy is 0. Let me see.
这个不在乎，是大概
Okay. 0.78, 0.85.
Yes.
0.88, 0.85.
你在哎，
0.88,
还好，对的。
0.85.
两算不太对，
So they both do better than the GRU, right?
而且高考这边写掉。
That they both do better than the GRU,
因为
right?
随便写
Yes.
Okay, go ahead.
可是我觉得你随便写可能也强过。
Guys, one at a time. One talks at a time. Okay, one talk at a time.
小杨子要考，去年限制
完全听不懂。
我靠你！
Guys, one at a time. Don't talk. Otherwise, it's already you don't have slides. If then you have 3 people talking, it's even worse. Okay, go ahead.
Okay.
Can you tell them to
Yeah.
shut up?
对呀，对，所以
We can see that it's trained well.
可是往往字数高，字数多人往往所以
And that's all.
Okay, very good.
关了，对啊，对，这样关了。
Yeah, guys, next time prepare some slides, okay? So you don't waffle on. Waffle.
没有，通常
Where is the noise in the background coming from? Yeah. Okay, good. Okay, group 1, are you guys back? Otherwise, we go to group 3.
Excuse me. We haven't
Oh, you haven't finished.
introduced
Go ahead.
RNN.
Yeah, group 2, go ahead. Group 2.
Okay, so some of the members haven't shown up, and we have a new member just because his
Yeah, I understand.
members also. So here's the code I have finished.
Go ahead. We are waiting for.
Okay. So this is my code, and everyone see the code?
Yeah.
So I have done the RNN and CNN part.
Mm-hmm,
And I am testing the RNN and CNN with the weight stacker in the optimizer of Ada.
Okay.
Just because you can see the overfitting is a little bit serious. We have 99% training accuracy, but testing only 78.
Of course.
Just because the model, we have built some.
Let me see. So this is the CNN.
And a mass pool, so it was simplified. So it can reach perfect accuracy just in 5 epochs. This is the RN architecture of embedding it.
So how many hidden layers? How many hidden layers do you have?
In RNN, we only have two fully connected. Okay. And for the CNN, we have 3 convolution, 2 max pool and 1 fully connected as output.
Yeah, good. Yeah. Okay, did you figure out what's going on with the RNN? Do you have some ideas?
Pardon?
So if you have any ideas of what's going on with the RNN, how would you try to?
For the padding test, and maybe I will do with for 2D CNN or for fully connected, just because the CNN I have demonstrate is an one-dimensional CNN. But I'm trying to figure out how will the 2-dimensional CNN will do.
How are you going to apply the 2-dimensional CNN? Because you just have a sentence, right? The sentence is a 1-dimensional string, right? How are you going to do the 2-dimensional CNN?
To reformat each word 1-dimensional, but into a 2-dimensional matrix. And for each word, we have a channel. So we have a stack of 2-dimensional matrix, right?
So you want to one-hot encode the words, or how are you going to do the matrix encoding? You're going to do one-hot
encode the words into 255 encoded embedding dimensions. So we can rebuild it into a matrix, and we have many words, right? These words will be a stack of 2-dimensional matrix. So we conduct the CNN, the convolution on each matrix, and we have many channels. So we can get another set of matrix.
So, but the word embeddings, do you plan to use some word embeddings, or just use the one that, because here the word embeddings are just integers, right? You could take some better word embeddings like bird or something like that, right?
Sure.
I think it's still not going to work. So yeah. So So right now, your GNN does better than the GRU, right? Which doesn't make
We
sense.
haven't done the GRU, but
Didn't we just saw the GRU? We just saw the GRU, right? The GRU was 0.78 on the short and 0.82 on the long, right?
we have INN and CNN right now.
But okay.
Thanks.
So, but are you group 2 or are you group 3? Your group?
Group 2.
But then, didn't before we saw this, the guy showed us the GRU training? But the guy that presented before, didn't he show me the GRU training?
GRU training, we haven't done it. So
So who was presenting before? They show me the GRU training. Was it group 2?
let me figure it out.
Before, the 10 minutes ago, right? There was a guy that was showing us the GRU training.
That's group 1.
I was group 1. Okay. Got it. Gosh, guys, you're so okay. Good. So you did the RNN training. You haven't done the GRU.
Yeah.
And the GNN, no CNN yet, right?
We have CNN and INN this recently.
So do you have the CNN results for me?
CNN results?
Yeah, can you show me the CNN results?
We haven't visualized, but we have the results like.
Yeah, tell me the test short and test long. Give me those two numbers.
We have the newer results of adding the weight decay, but I think the weight decay is a little bit too strong because we get the 86.5 training accuracy on CNN, but only 66.1 on testing. And for the RNN, we have it just have some problems. So
the RNN is not converging, right? So what did you say again for the CNN? What was the CNN test short and test long? Repeat those numbers for me.
Pardon?
The test accuracy of the CNN with weight decay. What is the test short and the test long? You just gave me some accuracy. Yeah, you just gave me some accuracy numbers.
Sorry, again?
Can you repeat those accuracy numbers that you just gave me?
The accuracy number before the weight decay. Here. 99.4 versus near 80. And this another result is added the weight decay of 1 in 1,000. So
yeah,
we get this.
You're not sharing, You're not sharing anything. You're not sharing your screen,
Sorry. Let me find out. Okay, so
that's good.
The weight decay is here. And after adding the weight decay, we get training accuracy of 86.5 and test accuracy of near 70.
But for long or for short? The data is split in long and short, right? So is this accuracy for long or for short?
For what?
The data set is split in long reviews and short reviews, right? Did you split the data set in long and short?
No, we have 50% 50%. So we get the
No, but you see the group before, right? You see that you have to divide the reviews in short reviews and long reviews, right? You didn't split the data set?
the data set we use is the
You should have long and short, right?
the IMDb, and I split
But
it into half and half.
No, but the length of the review, right? You should have the long review and the short reviews, right?
Longer view and shorter view.
Yeah.
What do you mean?
The group before, you saw the presentation of the group before, right? Right? You saw the group before, right? That they split the data set in long and short reviews? Because some of the reviews are only like 100 words, and some of them are like 500 words. So how do you do the padding here? Which line do you pad to?
Oh, for the padding part, sorry. The padding part is
So max length 500.
it's here. Padding with 0.
No, that's
padding,
a label. That is the label. That's a label. It's written label.
So I cannot find the.
It must be there. I just go somewhere. Just go. Keep going.
Parts of the part in the code, but I remember that I padding the empty things of 0.
I mean, but half of the challenge is like you pad before, you pad after, you pad with noise, you pad without noise. Like most of the challenge is about the padding, right? Right? And then you have to divide in short and long and see what is the performance of different network between short and long, right? Were you looking at the same file, or are you looking at some other files? Yeah. Right? You saw the group before, right? What they were doing.
Maybe some discussions is needed.
Yeah, I think so.
Sorry.
Trying to fix the. So you saw that most of the challenge was about how you pad, right? That you pad. You saw the group before that you pad with noise, you pad before, you pad after, right? You saw the presentation, right?
Yeah.
Have you done the part or not? Or you can just say no, right? It's just a question, or not. I'm just asking you if you did the part or not.
I'm just comparing with what do you mean by the thing, and I'm figuring out, is it fit or not? Does it fit or not?
Yeah, okay, but you understand the issue, right? So the issue is that the RNN, it's a sequential model. So it doesn't matter how long the review is, right? But the CNN is not sequential, right? So the CNN needs to have a fixed input, right? Do you agree on this?
A fixed input.
Yeah, the CNN is a fixed input, correct?
So the dimension of CNN.
Yeah, it's 500, right? It's 500 is there.
Let me find out.
There, right? Right? Because the length of the sequence is 500. The maximum length of your sequence is 500. Right?
So before feeding into the CNN, I have padding all sentences into the same length.
Yes, but with the RNN you don't need, right? Because it's a sequential model. Correct?
Correct.
So the challenge was about that, right? Was about the fact that RNN and GRUs, they are more, they're harder to train, but they can work on sequential data. But the CNN, it's more stable to train, but you need a fixed input. And so then the next part of the challenge was about how you can vary the performance with different type of paddings, right?
Sure.
Okay. So try to get it done by Friday, okay?
Okay.
Good. Okay, so group 1 we did, group 2 we did. Right. Yeah, let's go group 3.
Can you hear that?
Yeah.
Okay. Wait for me. Can you see the slide?
Yeah.
Okay. Hi, we are group 3. Today our project is about dealing with natural language. We'll use 3 models, which are CNN, RNN, and GRU. Besides, we use INDB dataset to train these models. There are some details during data pre-processing, and that's why
Can you go in presentation mode? Sorry, can you go in presentation mode so we see a little bit better? Yeah,
okay.
presentation mode. Yeah.
Where?
右边。
按那个投影播放啊，投影播放在右上角。
Oh, okay. Sorry.
Good.
This is the first time I use this one. Okay. So we are going. I am going to introduce the data pre-processing part, and including tokenization, padding, and shuffling. So the later part will introduced by my member. Okay, so first we need to load in the data set with INDB load. This is included in TensorFlow Keras dataset, this package. And if we use this one, we can load the data set into our notebook. And you can see that there's a lot of package imported here, and including Keras preprocessing sequence, and including NumPy, of course. And besides, we use. Oh, sorry, wait for me.
Where are you going?
I need to recording.
那你要先从前面开始报吗？
好，我重来一次。Sorry, I can I restart again?
Of course, I mean, you can do whatever you want.
So we want to record it and just record it as a video and then just can save on.
Because I'm also recording, right? So why do you want to record it yourself? Huh?
Yes, just record it as a video.
Good. It's a good exercise to look at yourself talking. Right? It's a very good exercise. Go ahead.
Okay, sorry. Hi, we are group 3. Our project is about dealing with natural language. So I will introduce the data preprocessing part here. And our proposal is to understand natural language processing, which are CNN, RNN, GRU. And besides, we use IND dataset to train these models. There are some details during data preprocessing, including tokenization, padding, and shuffling. Okay, so first we need to load in the dataset with INDB load function, which is included in TensorFlow.keras.dataset.INDB. And you can also see that there are other functions imported here, including preprocessing.sequence and of course NumPy. And also we have used some helper function, currently sample 10,000 entries from the full training and testing set, which proposes to shuffling the data set to avoid overfitting. Okay, instead I will introduce what tokenization and padding is. Okay, so tokenization is to transform natural language into positive integral number. So it means that every single review will transform into a series of positive integral number, like the figure show in the right hand side. And
Question. How would you do the labeling? How do you think the labeling is done? Who decide what's number 1, what's number 2, what's number 3?
I only know that number 1 means star and number 2 means unknown, and other labels will have a specific vocabulary, but I don't know what does that mean.
But do you? I mean, you saw in the previous two presentations ago, right? That one, like 3 was the, 4 was a, 5 was he. You know.
Yeah, I know.
So,
I know it has a specific meaning. It means that the frequency.
correct.
Yeah.
Correct.
I mean, I know that the smaller number means that it's how frequently appear in the dictionary. So
correct. No, in the text, right? So the dictionary, everything appears once, right? But yeah. Anyway, so the frequency in the text. Yeah.
yeah. So
in the dictionary only appears once.
Yeah. So after we finish the tokenization, it will become a series of a positive integral number, and we will have a specific length of a series. But however, if we didn't standardize the tokenized review, every review will have a different length. So we need to do padding, which is in order to standardize every single reviews. So the padding we use is free mode here. But of course, we have different kind of padding mode, which is include center and also include post padding. And we also can pad it with different value of number, because we use 0 padding here, but we can also padding with random number or 1. This is another padding method we will discuss in 6.0.1. Oh, 6.0.2. Yeah. Okay. We can also adjust index to reverse specific token. So besides, a reverse mapping is created to translate index back to a word, so we can know what the specific meaning of this number represent. This part is tell you that the sample review show in this slide with 1 a start. It's why I say this one. And the pre-padding and post-padding part is also explained previously, so I will skip. We define threshold to differentiate between short and long review. Because we want to train it separately, we need to set a threshold, right? So we will need to separate the two kind of different data sets. So we finished setting the threshold, creating separate subsets. The label for each subset are converted to NumPy array to ease the use in model training. So after finish padding and tokenization, we finished the processing part so far. So we will compare different deep learning architecture utilizing helper function for training, evaluation, and other visualization. Okay, so next part is other group member.
Hi.
Hi.
So, 帮我跳下一张。这边还是你吗？还是你直接再跳到 RN？
那个图讲一下吧。
你讲吗？还是我讲？
你也可以讲，反正没关系。 It's okay, right? I mean, it's clear. Go ahead.
This part is actually his, but
You can tell us. It's okay. It's clear, right? The message is clear.
yeah. So CN is it can train very well, and we can see that with short data set, that performance is it's not better. But this is different from in ARM and GRUs.
But
So,
okay. So, but here you see that, like, does it make sense to you here, right? So it's clear that there is an issue with the input length, right? So if you had to have an even longer input, right, then you will expect the accuracy of the CNN to go down, correct? You see that the shorter has a better accuracy, right? Then the longer has a lower accuracy. Does it make sense or not in your mind?
actually, the short one has worse accuracy in the plot.
Oh, it's a loss. Sorry. It's a loss. So the short has a wait. So because from the validation loss, just a second. Validation loss, long validation loss. So the left one. So what's the difference between the left and the right? Oh, that's the accuracy. Okay, sorry, the accuracy. So you saw that the short accuracy is lower than the long accuracy. Okay, good. So that's so let me see again on the left. What happens on the left? On the left, we have short validation loss. Right, it's higher than the long validation. Oh, sorry, I'll take it back. So this one trains better. Good. Okay, go ahead.
I think it's because the short has less words, and therefore it didn't train very. It didn't get trained largely, and
The
that's
data
why
set is balanced, right? You balance the data set, right? They both have size. What's the size of the data sets? Is roughly what, 8,000? What's the size of the data sets?
I think it's about the same.
It's balanced, right? Okay, good.
Yeah, and you can see that the training part, which is the blue line, short is not worse than long data set. But in validation part, short data set is worse than long data set, and I think this is because the short one has less information. Since
Okay. So that's the balance, right? Because you expect, like, semantically, right? The longer reviews should reveal the sentiment better. But then the network with the network for long will have more parameters, so it will need more data to train, right? So that's the effect that you expect to see, correct?
Yes.
Okay, go ahead.
Okay. So next slide. So here are the 5 things we do to build our R model. First, we enable max zero in the embedding layer to ignore padding tokens. Otherwise, the model will be hugely affected by zero paddings, causing the output to be 0 every time in post-padding mode and bad performance in pre-padding mode. Okay. Second, we employ bidirectional RNN to capture dependencies in both forward and backward directions, which is helpful for language processing, as understanding a word often depends on both its preceding and following context. And the third is dropout is used to mitigate overfitting, which is a common issue in RNNs. And later I will talk more about this. And the fourth one is the dense layer to process the features extracted by RNN, and one final sigmoid activated neuron to output the probability representing the sentiment. And the 5 is to keep the whole network as small as possible, since ARM is very prone to overfitting, especially on small data set like this task. So here I want to talk about why ARMs overfit easily. So a single layer ARM with D neurons, which take k embedding dimension, can be expressed as follows. So the trainable parameters is a significantly more than typical feed-forward networks. So this increases the risk of overfitting. And also, ARMs are designed to remember patterns across time, which makes them prone to memorizing patterns in training data. In addition, IMDb Mini is relatively small, so this further increases the risk of overfitting. And since the test is binary classification, the model can easily achieve high training accuracy, but not high validation accuracy by picking up superficial patterns rather than learning meaningful semantic representations.
Can you give me an example of this? Can you give an example of this?
An example.
Yeah, just from the English word that you use generally.
Can you repeat?
Yeah, just from your daily use of English. Can you give an example of this in the English language?
You mean the third point?
Yeah.
Oh, so maybe it just sees one word like bad, and it just output it's a bad review.
But now give me an example in which you can say bad to mean good. Go ahead.
Okay.
Give me an example. You can say, oh, this movie is bad, so clearly it should be negative. Now give me a positive review that uses bad as give me positive reviews that also contains the word bad. Go ahead.
This movie hurt me so bad, I cried. I cried in joyful tears.
Good. Yeah.
Okay.
Because that's usually there's some more neutral maybe example. You can say terrific. I can say, oh, this was a terrific movie. Or you could say, oh, going to see this movie was a terrific waste of time, right? But this is exactly what this is exactly what I was asking.
That's a better example. Okay. So next slide. And after 1,000 times of trial and errors, this is the final model we come up with. And the key point is small, to keep the network as small as possible, and a relatively small learning rate, and batch size not less than 64, because small batch size also increase the risk of overfitting, since the loss calculation is easier in small batch size. Okay, so next slide. Since mass zero is enabled, the disadvantage of short sentences, which is lot of paddings, is mitigated. As a result, the model now performs better on shorter sequence, which is different from the previous, the CNN ones, since long sequences now face other challenges like vanishing gradient or long-term dependency. So in the plot, you can see that the two curves in short sequences are better than long sequences. The short sequence is a solid line, and long sequences is dashed line.
Is this averaged, or is this averaged?
Average, you mean multiple trainings and average?
Yes, multiple initializations.
No, but we
Okay.
see
No,
these.
just a question. Go ahead.
Yeah, so now the short sequences are trained better than long sequences. Okay. Next slide.
Do you want to explain maybe the vanishing gradients? Do you want to try to explain that a little bit? Because it's a different than the usual vanishing gradients, right? Do you want to try to explain it?
Okay, so when the sentence is long, let me think about.
Just if you want, right? So we're gonna go through the slides, right? But if you want to try, go ahead.
So there are two kinds of scenarios. One is gradient is explode. This is when the parameters are bigger than 1. So after each time step, it get multiplied by a value bigger than 1. And with long sentences, eventually this will cause the output to be very big. And with parameters values less than 1, this will cause the output to vanish, because when the sequence is long, it get multiplied a lot of time. Eventually, it comes near to 0.
I think what the point here is that when you do backprop, right? Backprop goes across the length of the sequence, right? So when you do backprop over longer sequences, you are backpropping over longer steps, and then this is where the numerical instability comes from. Because usually when we do backprop, the input of the network is fixed, so we just go from bottom to top. But when we do sequential, then we go from end to beginning, right? So the number of backprop steps depends on the length of the sequence. That's what you were.
Yes. So yes. So,
okay, go ahead.
Okay, so here are GRU motivations. Since RN suffers from vanishing gradients, which makes them struggle with long-term dependencies. That's why GRU introduced gating mechanisms to control memory flow adaptively. And so they introduce reset gates, which decides how much to forget by controlling previous state in the computation of a candidate state. And the candidate state is a proposal for a new state, which is controlled by reset gate, and later mixed with previous state through update gate to produce the final output. And the update gate decides how much to keep from the past memories, which is the previous state. So it controls previous state and the candidate state in the computation of the final state. So this is the gating mechanisms. Okay, so next slide. And training GRU is a lot easier than training ARM, and it takes us almost no modifications for the model to work. So the structure is the same as RNN, just with bidirectional removed. And this proves the GRU's superiority over RNN in sequence modeling task. So the plot is basically the same as RNN, but this is it takes us less time to come up with these results. Okay, so my part is done.
Okay, and it's probably. And next part, and the last part is padding strategies, and we have do some experiment for it. And in this graph, it shows 3 different padding modes: pre, post, and centered. These 3 different kinds of padding modes at the same set of shortage fields. And the custom padding extend based on the basic era pad sequence to also support centered padding. And then the CNN model will be built and trained and separate for each type of paddling type. And the result come out that the pre-paddling has the highest time. And
Pre-padding, not pre-paddling. Paddling is
pre-padding. Yeah, pre-padding have the highest time. And then the last time is this time is the post-padding. And also, since that it takes the latest time, it also has the highest accuracy.
So here, how did you calculate the time? Did you fix the number of epochs, right? Yeah, you fix the number of epochs, correct. And this is only for the CNN, right? Because for the RNN and GRU, you have the masking, right? So that's why you didn't test it, correct?
Right. And next page. And I'm going to quickly talks about the padding. Zero padding is the traditional method where padded positions are filled with 0, and one padding is that where padded positions are filled with 1, and potentially signaling with different significance to the model. And then random paddling is where padded positions are filled with random integers. Yeah.
Padding, not paddling, okay?
Padding, okay, padding.
It's just fun, whatever, right? It just, do you understand what is paddling, right?
Yes.
When you go with the boat, right? You are paddling. That's
Yeah.
a different word. Question: why do you think there is a difference? Why do you think there is a difference between the 0 and the 1 padding? Right? Shouldn't it be the same because it's a constant value?
Different with 0 and 1 paddling. Let me think.
I think maybe 1 represents star, and we often use 1 as a star, so maybe it will because some noise. And I think 0 padding is better.
Yeah, it's a numerical stability thing, right? It has to do with numerical stability, right? Because you see that you have a lot of matrix multiplications in the model, right? And then your activation function is the sigmoid, right? So but anyway, so you do understand that it's numerically it's different, right? Because multiplying by 0 and multiplying by 1 is not the same. And also in terms of computational efficiency, right? Because if you're multiplying by 1, you still have to compute the result of the multiplication. But if you see a 0, you don't need to calculate the multiplication, right? But there is also a numerical efficiency, right? So yeah, it's a purely numerical consideration. Okay, go ahead.
And I also think that it will have impacts on probably masking conditions. That 0 padding, because it adds 0, so that the models will just learn only from actual tokens. But when it's 1 padding, then the model may learn from the model. I think the model that the position will not be like 0 padding be automatically masked.
So, but because in a sense, the masking that you guys did, it's adapt. So, as we said, right, RNN, GRU, LSTMs, they're all sequential models, so they do not need the padding in theory, right? So we pad the sequences just because we want to adapt the input to a network with fixed input size. So in a sense, the masking remove what we added for different types of networks, right? So we do padding in order to fit the sequence into a network with constant input. But for sequential models, you don't need the padding. So, the masking will not, we will not apply the masking if we're using a sequential model. It was more for you guys to observe the differences, right? Anyway, go ahead.
Oh, okay. And probably next page. It'll be the results. 0 training accuracy and 0 validation accuracy.
Okay, this is for 0 padding, right? Okay, good.
And next part. And then we've tried we've tried advanced padding techniques, like we do experiment to the sequence dense, range of mass sequence dense are test, and then we find out that the higher the sequence dense, then the validation accuracy will go higher.
Question. Let me think about this, right? So this is always CNN, right? So when you change the sequence length, do you balance the data set when you do this experiment? You know what I mean, right? Because if you increase the sequence length, the number of elements in the data set that are lower than this maximum sequence length also increases. So my question to you is, did you normalize the data set length for these experiments?
Normalize it.
I think we didn't do this one. Yeah. We didn't
Because you see that
normalize.
then it's an unfair comparison, right? Because you can imagine that, as the sequence length increases, you have more elements in the data set. So it is not clear if you're seeing a better training performance from the effect of the increased information, which is in long sequences, or if it's because you have more elements in the data set. So we do these experiments, but always subsample the data set so that you have the same number of sequences in the data set.
All right.
Make sense?
Makes sense.
Okay, go ahead.
And next, it's doing the experiment, and the result is shown as the figure. And next page. Next one we do the vocabulary size experiment, and different vocabulary size, 1,000, 5,000, and 10,000. And we've shown that the higher the vocabulary size, then the validation accuracy will gonna be higher.
Let me think about this, right? Because this is also complicated, right? Because when you increase the vocabulary size, right, you turn some unknown tokens into known tokens, right? So how could you normalize the data set so that you can see the effect of having a larger vocabulary set? You understand my question, right? You understand what I'm thinking, correct?
Well, it affects.
Yeah, but it's like, what type of experiment would be fair, right? For the previous slide, we said, well, if you increase the length, then you have more sequences, then the data set has more information. Good. Here we're saying this, right? When we increase the vocabulary size, we're changing some tokens from unknown to known. Is this clear?
Yeah.
So you're introducing more information into the model. So in a sense, you would like to see the effect of the vocabulary size as when the fraction of unknowns remains the same, right? Something of that sort. What would be a fair way of comparing this? Like, you're feeding more information into the model, right? So you would like to see the effect of the size of the data set alone, and not from the tricky. Yeah, I don't have an answer. You understand what I'm thinking, or am I just confusing you?
Let me think.
Because I'll tell you what I would do, and then you tell me if it makes sense.
Okay.
I will look at the distribution of the tokens, and I would see what is the percentage of tokens that are unknown. Then, in order to compare two different models that have two different embedding sizes. What I would do is that I will keep the percentage of unknown tokens to be the same in the two datasets.
Like to keep the experiment in a fair condition.
But I'm not sure. Because you see, when you increase the token size, right, you're not increasing the complexity of the model because the inputs remain the same.
Yes, like we also write it out that the varying vocabulary size might affect the tokens appear in the data sets. So
yeah, because you can learn more. Yeah, you have more. You just more information into the model, right? So it's not fair in that sense. Yeah, I don't have an answer. I think it's
due to this, we also write it in the report. Just write a sentence like
because it's clear that
we didn't think that
it's just a discussion, right? It's just a discussion that we're having, because it's clear that there is a jump in complexity. Let's say when you go from 16 bits to 32 to 64, right? So of course, like let's say for the 1,000, the vocabulary size of 1,000, right? You can have it in the 2 to the 8, right? So you just need an unsigned 8. But if you go to 100,000, then you have to switch to 16 bits. So of course there is a complexity that comes from the representation of the number in terms of bits. So that's one aspect of complexity.
Oh, okay.
And of course, the more tokens you have, the harder it is for the model to learn the patterns. Yeah, no. I mean, it's just a discussion. Yeah, no. I'm not telling you to do anything. I'm just thinking, because what you would like to see, you would like to see how much accuracy you gain by improving the vocabulary size, and you would like to take out the other aspects of this, right? And if you change the vocabulary size, what happens is that you turn unknown tokens into known tokens. So you would like to take the fraction of unknown tokens out of the equation. So you keep the same fraction of unknown tokens. But again, it's a complex process, and we're just discussing a fair comparison in some aspects. So yeah, just go ahead. It's an interesting issue.
Okay, perfect. And next page. Yeah. And we also do an experiment to the word frequency. Like we've only we filtered and we counted only 10,000 most frequent words that affect the model performance. And then we've filtered out the tokens that are less informative. And then that we will print out the final validation accuracy. And then it turns out that the accuracy with filtered vocabulary based on word frequency is 0.88. It's not. It didn't really have a very efficiency, but it just a little bit.
Yeah, the loss is not that big. Yeah, that's what you're trying to say.
Right.
So here I understand. So let's I think it's like this, right? So the tokens number is based on the frequency over the whole English language, let's say, whether the frequency that you consider here is over the frequency of the data set only, right? So it's some sort of fine-tuning, correct? So the frequency that you're discussing here, right, is the frequency over the data set, correct?
Yes, I think it's correct. Just with just only filtered out the words.
Based on the data set that you have, yeah, good. Okay. So here, let me see, tell it to me, repeat to me. So what is so you start with the 10,000 most frequent, and then you just choose the 10,000 most frequent in the data set, correct? And then you compare the two accuracies. Is that correct?
I'm not sure about your question. I'm not sure about the questions. Could you say it again?
Okay, so this is my understanding of what you did, right? You took the tokens between 0 and 10,000, you train the model, you get an accuracy. Then you go into the data set, you look at the 10,000 most frequent words in the data set, and you only, you create a vocabulary with the 10,000 most frequent words in the data set, and then you compare the two accuracies. Is that correct?
Right. Just we've just compare with it, right?
Okay, good.
And
so what's the conclusion? That you have a better, yeah, go ahead. What's the conclusion?
The conclusion is that we have a bad, but it has a better frequency, but only a little bit higher, because the original is 0.885, 0.88449. It's only
Okay.
it only improved a little bit, just a little.
0.1%. So you're saying.
Yes, probably. Next page. And and here is our evaluation metrics. That is a conclusion of all things about.
This is with CNN.
Yes.
Yeah.
With
And what's the dictionary size here?
Size is
50K.
Size, and check the original code. Size.
Because I would have expected more differences, right? And your accuracy is BCE, right? So it's still going down. It's still training. And train and validation are one on top of the other, which is also not fully what I expected.
It's
And because you saw the other group. Go ahead.
Okay, and next page is the accuracy. And then and down is also the paddling and its training time.
Yeah, I would have. Usually there are bigger differences, right? Of course, it depends on the architectural depth and so on and so forth. But yeah, usually there is a bigger difference. You show that the other groups also have a bigger difference. Just a comment, Just a comment.
Oh, okay. And this is all of our
Okay, good. Okay, guys, let's take a few minutes break. I'll give you 10 minutes, okay? So I'll see you back at 50, and we go with the next group, which is group 4, okay? Go take a break, walk around, drink some water, okay? Ciao, guys. So guys, have you seen, we have 2 minutes before we go, huh? Guys, have you seen the news regarding Harvard? Have you seen the news today regarding Harvard? Right, because we're using their course material, right? So we are connected to them in some ways, right? Have you seen the news? Guys, have you seen the news or not? Nobody? Guys. Yes, I don't want to be political, okay? I'm just showing you the news. I'm not doing any political commentary, right? Yeah, so this is the because there is this DEI fight in the US, right? Diversity and inclusion fight. And the current administration asked Harvard to revisit some of their policies. And of course, the tool that they have is federal funding, right? So the US is a federal state, right? So there is money at the national level and money at the state level. And the president controls the money at the national level. So he freezed some of the funding, $2 billion of funding for Harvard University to obtain this, right? And yeah, you know, the of course, it's always about Trump in the last 2 months. And so it's an ongoing fight because, you know, let me show you something. Yeah. So because Harvard has just a second. Let me see if I can find. See if I can find the article. Let's see this one here. I just want to show you something, right? It's a longer discussion, but just something for you guys to discuss, right? Because, you know, going to universities, it was always like in the 1920s, the 1910s, right? Going to university was just an affair for rich people, right? So rich people will go to this Ivy League university in New England, in Massachusetts, you know, and it was just something that rich people will do, right? And then Harvard has been the first one to open the doors to a different group of people, apart from rich white people. And the Jews were the first one to enter into Harvard. So there was this idea that there were a lot of Jewish people from New York that would go to Harvard. And then they had the first quotas for how many Jewish people will be accepted into Harvard, right? And then there was a big discussion about this. And then eventually, after the Jews, also black people started being accepted into Harvard, and Harvard has some very interesting policy about letting black people into university. And apart from the political aspects, I think it's interesting for you to think about this type of issues, right? So if some group of people should be granted access to university, not only based on merits, but because maybe they come from some disenfranchised parts of the population, right? So it's a long discussion. There are many things to be said, and I think it's just interesting because you guys maybe don't think about this because Taiwan is a smaller country, doesn't have some of the problematics that bigger countries have. But you can imagine that there are students that come from, for example, immigrant families, and for example, the admission to university values a lot the knowledge of Chinese, and maybe if you come from an immigrant family, then you are disadvantaged there. And yeah, there are many interesting things to think about. Anyway, Nothing political. Okay, very good, guys. Group 4. Okay, go ahead, group 4. Tell me something.
Can you hear me?
Yeah, of course.
Wait a second.
Let me ask you, what do you think is the DI policy that NYCU should have? Is there any disenfranchised or disadvantaged group of students that you can think of? Okay, that's good.
Okay.
It's only you? Group
First,
4 is only you?
I apologize because I cannot contact two of my members, and one of the other member had been transferred to other groups by the TA, so I basically done all the things myself. So due to the time limit, I cannot have a very complete presentation. So I will try my best. So and I will refine the the report after this presentation. So I apologize for that. So okay. So today I'm going to present the results of a deep learning experiment focused on sentiment analysis using IMBD movie review dataset. And I explore how different neural network architecture, CNN, RNN, GRU perform on text classification tasks, and more specifically, how they handle short versus long text sequence. And additionally, I ran a series of experiments to test the impact of different padding strategies on model performance. And padding is often treated as a trivial processing step, but as you will see, it can significantly influence the learning dynamics and of sequence models. Okay, okay, let's delve into the models and results. Okay, so I will briefly go with my code. Okay, wait a second. So the first Python script builds and compares different deep learning models, CNN, and GRU for sentimental classification on the IMBD movie review dataset. So we begin by loading the IMDb dataset with 10,000 training and 10,000 test samples, and each review is converted into a sequence of word indices based on frequency. We apply post padding to standardize review lengths to 500 tokens. The data is split into short reviews less than 100 words and long review 100 words or more.
So your threshold is 100. Okay, good.
So we implement I implement three architectures, each with a neural budget of k equals to 10,000, excluding embedding layer. The convolution neural network CNN extracts local feature using multiple 1D convolution layer, and it includes three convolutional blocks: global max plotting to flatten the output, and dense layers to classify the sentiment.
To one neuron. Yeah.
The recurrent the recurrent neural network is built with two simple RNN layer, each followed by dropout. Dense layer for a dense layer for classification. Each model is sequenced by processing one word at a time, but may suffer from vanishing gradient. And GRU, or a gated recurrent unit, is smarter RNN with gates that helps retain long-term information. And two GRU layers are used, and it's generally more efficient and performs better on long sequence. And each model is trained on both short and long refill subsets using train and evaluate function. And I apply early stopping to prevent overfitting, and validation split of 20%. And accuracy and loss are tracked over epochs. And trained models are saved and visualized in a learning curve. So after training, the analyzed by lens function evaluates how each model performs across different review lens intervals, such as 0 to 50, 50 to 100, up to 500 plus. And each group's prediction, calculate accuracy, and plot the result. And finally, I collect all test accuracy for each model and display them in a bar chart. And this gives a side-by-side performance comparison of all models across different review lengths. Okay, second. Okay, so the first picture is CNN unshook review, and left part is accuracy, and we see a rapid increase in training accuracy surpassing 99% by epoch 9. And validation accuracy rises to about 83% and then plateaus, indicating good generalization but some room for improvement. And the right part is loss. Training loss drops steadily, but validation loss increase after epoch 4. This indicates the model is overfitting beyond this plot. So CNN learns well on short input but tend to memorize the training data if trained too long. The next one is CNN on long reviews. Okay. So the model reaches over 97% training accuracy, and validation accuracy stabilize around 80%, showing strong generalization. And similar to the short version, we observe a validation loss increasing after epoch 4, epoch 5, again hitting at overfitting. So CNN works impressively well, even on longer sequences, but should be trained carefully to avoid overfitting. And both next one is on short reviews. Both training and validation accuracy remain around 53 to 57%, not much better than random guessing, which is 50%. And the loss curves are mostly flat, indicating the model fails to learn meaningful feature. So the standard struggle with short sequence and may suffer from gradient issue or
what's your batch size here? What's your batch size?
Batch size.
Yeah.
Okay. Wait a second.
Yeah, because you're not learning, right? So you have to do the experiments as the
64.
before, right? 60.
I
Yeah.
use 64.
Yeah, you have to.
I haven't adjust the batch size to test. Maybe I can do it later.
Of course. Yeah. Take down the learning rate, switch to Adam, play with the batch size. Yeah. So there is no learning, right? So go ahead.
Next one is on long reviews. The training accuracy fluctuates between 49 to 51%, and the validation accuracy hovers at 51 to 50%. And again, it's very poor. And the loss decreases slightly, but not significantly. This confirms that the model fails to extract sequence level pattern. And so RNN fails to learn and long sequence, and likely due to finite gradients and limited memory capacity.
Yeah, so let's try to adjust this, yeah? Yeah, so this also the GRU is not learning. Also the GRU is not learning, right?
Yeah. So I'm going to talk about the GRU. So yeah, it slightly outperforms the RNN and achieving about 55% training accuracy, but it's the loss decrease only marginally suggests weakening signals.
But you see here also the validation accuracy is still this 0.57. And the 0.57 could come from the fact that the reviews are not balanced, right? So it's possible that the ratio of zeros and ones in the dataset is not 50%. So the random guess gives you the 57, right? Because you saw there was validation was 57 before and it's 57 now. So I think it's just not learning, right? I think it's also this model is not learning. Go ahead.
Okay, so the next one is GRU on long reviews, and the model shows a much stronger learning compared to the previous ones. And both training and validation accuracy increased rapidly and plateau near 88 to 94%, in which the both losses drop sharply, and validation loss showing minor fluctuation after epoch 6 and indicating good generalization. So GPU performs best on long sequence. That's confirming that its gated memory structure helps capture long-term dependencies effectively. So here's a comparison. So CNN are powerful and generalize well, especially on short to medium sequence. And ARM struggles regardless of input length, and GRU requires stronger input to shine, where they achieve state-of-the-art performance by retaining important sequence memory. Here's the here's a visualization of the previous result. Okay, I will go to and I'm going to move on to the padding experiment. So this script explores how different padding strategy impact the performance of a GRU-based sentiment classifier trained on the IMBD movie review data set. Pattern is crucial in NLP because models expect input of equal length. And these experiment tests not only where we apply the paddling, like before, after, or center, but also how we apply it using custom values and even artificial patterns like noise and reflection. And our data, we use IMDb mini.pkl file to load processed IMDb data, and which contains tokenized reviews and their sentiment labels, 0 for negative, 1 for positive. And pad sequences ensures every review of fixed length, which is 5 tokens. And if the file is missing, the data set is downloaded directly using Keras and set locally. And so now I define several functions to apply different paddling strategy to the review data. So standard paddling is apply paddling strategy support pre-paddling, paddling at the beginning, post paddling, paddling at the end, and center paddling. Balanced paddling.
It's before, right? So there is padding and paddling. So here we're talking about padding. Paddling is something.
Padding, pre-padding, post padding, and center padding. Yeah. So the center padding, balanced padding on both ends. So it's a custom implementation. Then padding by value. The function create value paddings generate 0 padding, 1 padding, and random binary padding, which is zeros and ones in random order. And have advanced padding. The function create noise padding as Gaussian noise instead of zeros, and create reflective paddings pad the input by repeating and mirroring the original sequence, mimicking reflective behavior. And I use a gated recurrent unit GRU model because it is efficient and effective to for sequence data like text. And the model architecture includes an embedding layer, 2 stack GRU layers, 128 and 64 units, and dropout layers to prevent overfitting, sigmoid output layer for binary classification. And the train and evaluate function, it compiles, train and evaluate each model using validation accuracy as the primary metric. I also use early stopping to avoid unnecessary overfitting. So there are 3 experiments. Experiment 1 is different padding position. experiment 2 is different padding value, and experiment 3 is some advanced technique, which is always which are noise padding and reflective padding. Okay. So, okay, I will show this name. So, let's start with the first experiment, where we compare padding position, and the pre-padding results in a high validation accuracy of 88.4%.
Sorry, which
And-
network is this? Which network is this? The CNN or which network?
Sorry, can you? I use GRU.
This is GRU. Okay. And
Yeah.
so this is the long data set. Which data set is it?
Long data set.
So this because before you had 80%. Okay. Yeah. Because before
Yes.
it was just learning for the long, right? Because
Yeah,
then,
the short one doesn't work. So the pre-padding result in a high validation accuracy of 88.4%, showing strong performance. And post-padding dropped drastically to 51.6% and nearly random guess. And center padding performed similar poorly at 51%. So GRUs perform best with pre-padding, likely because padding at the beginning allows meaningful tokens to appear later in a sequence where GRU are more attentive, and post and center padding push meaningful information too early or dilute in the middle, leading to poor learning. Okay, next is experiment 2, padding values 0, 1, and random. In the second experiment, I invoked how padding value reflects learning. So 0 padding is a common default, it's 51.5%, and 1 padding is 51.8%. Random binary padding is 50.7%. So changing the padding value does not significantly improve the performance. All variants hovered near 50%, showing that it's not the padding content, but where it's placed that really matters, at least for GRU. And so for experiment 3, advanced padding, noise and reflective. So noise padding at only 50.5%, showing no benefit. Reflective padding, 88.6%, best performance overall. So reflective padding surprisingly performed even better than pre-padding, achieving nearly 89% accuracy. I think it is because it reduces patterns from the original sequence, possibly enhancing context and reducing signal loss. And it's also the GRU to process meaningful tokens even in a padding position. Okay, so here's the visualization of the previous result. Okay. So to wrap up, this study provides some clear insight. CNN are reliable and perform well across short and long input. RNNs are struggles in both cases due to their limited memory and gradient issue, and GRU performs poorly on short input but excel on long reviews, especially when paired with thoughtful padding strategy. And I also found that padding matters, not just its position, but even its structures. In particular, reflective padding and pre-padding led to significantly better performance than post-padding and random noise. And these experiments highlight how important model structure and data preparation are in building successful NLP system. Okay, so thank you for listening.
Yeah, thank you. Yeah, so try to improve by the submission, try to improve the convergence, try to play around with the edge size, learning rate, and so on. You can also add some weight decay or whatever. Just try to make the other models learn. And then these experiments for the padding, also do it with the CNN, please, okay? Because CNN is where it's most critical.
Okay.
Okay, very good.
Okay, I see.
Group 5, go ahead, Group 5.
Hi.
Hello.
Hi. So I may show my
Hello.
screen.
Go ahead.
你要秀还是我秀就好？还是等一下
我来
你秀完之后再换我秀？好，你秀。
可以啊，可以啊。那我先秀。
嗯，
Okay. Okay, so we are group 5 and we are gonna report the challenge 3. So first we have our member participation. So some of member did not do actual work. So one of the member disappeared and we believe he withdraw. And another member is busy for other things. So he is still active, but just discussing the model, but not doing actual work and presentation. So actually we have only 2 members in this group. Okay, so here's our outline and we divided to 3 parts. So I'm gonna introduce the data preprocessing and the model training, and other member will talk about the padding compare. So first, here's our code for data preprocessing. So first we get the data from IMDb dataset, just here, and we randomly choose 10,000 data from the training and test dataset, and we do the preprocessing here. So we print out the shape of different variable.
Mhm.
So next we segmenting the data set to shorter and longer reviews. And we segmenting in 2 ways. So first we use 10,000 data and divided to 1.1K samples for short reviews, and then the other for long reviews. And if we're using 25K training data, so we have this number of samples. And next we check what we have. So we just show the information after padding. Yeah, and the label refer to the training
Sentiment.
data. Yeah. So that's, and next we do the decoding. So since we need to reserve the place for the special things, which is 0 to 3 for the work index. Yeah. So that's the result of the decoding. Okay, next for the code for model training. So here's the basic model for 3 models. So we set the approach to 5 and batch size to 32. And we use the adder optimizer. So next we have the CNN.
Can you go back to the last slide? Yes.
Okay.
So here is the final version of the train and evaluate model. I have tested 16 batch size and 64 batch size and 10 or more epoch, but overall 5 and 32 batch size performs the best overall. So I choose this final edition.
Yeah. So next we are gonna introduce the CNN. So we use a convolution layer here with 128 neurons and doing max pooling and
Filters. Right? So it's on neurons, it's filters. Yeah.
Yeah. And we do the max pooling and dropout layers, and we pass a dense layer with activation value activation function. Yeah. So here's a related code. So here's the result of the CNN. So we can see that the accuracy is quite high in all of the situation. So even in short tests, we have 82.5 accuracy after training. And if we use 25K training data, the short test increased to 89%.
Wow. So the
Yeah.
full data set does better than the short one.
Yeah, here's the full data set in CNN. Okay, so we try a lot of times. So, we just choose one good result of CNN. Yeah.
Mhm. Let me see. Just let me just a second. Stay here a second, right? So when you do the short reviews, what is the 10,000 after the label? You say best CNN short reviews. 10,000. Is that the dataset size, or is that the what is it? The 10,000 there?
So here means the short.
Here. So
Yeah, this one.
this one. So the total
The short.
number of short plus long reviews is 10,000.
Okay, good.
Yeah.
So when you put them together, you do the padding up to 500, right?
Yeah.
Yeah. The length of the sentence is 500.
And here you're doing the. I mean, for the short one, you can do shorter. You don't need to do 500 padding, right? So when you do the short one, do you also have a smaller model or not?
We both do 500 links.
Yeah.
That's my point, right? That's my point. That's why you don't see a difference between short and long, because with the short one, right, you can just take you don't need you can pad to 100, and with the long one, you can pad to 500, right? So the idea is that the shorter ones, you can have a smaller model that can learn better, right? So that's what I wanted you to experiment with.
So
does it make sense?
Yeah.
Just do this test, right? It's not a big deal, right? You just have to change one hyperparameter, but that's because you don't see any difference, right? Because in my mind, I wanted you to see that, like the CNN. So of course, you don't use CNN for NLP, right? So the idea was to have you experiment with a model with a fixed input, so you can see the effect of the padding, right, on the model of the two sides. Because if the sequence is very short, and you have to pad to infinity, then there are a lot of neurons that you don't use. So you're increasing the model complexity for anything, for no gain, right?
Yeah.
So please redo this experiment, because that's what I wanted you guys to see, okay?
Okay.
Does it make sense?
Makes sense.
Yeah. And
Okay,
actually, the other teammates have done this, but he just doesn't have time to write what he got inside the PowerPoint.
No problem.
Yeah.
You said that he's going for the interviews for his master, right? So it's important.
And he has done the length part.
Yeah, because that's what I would expect, right? So there is this trade-off that I want you guys to see, right? The size of the data set versus size of the network versus effect of the training. So try to add it in your final report, okay? Go ahead.
Okay.
So next is for the RNN. So for the basic information of RNN is that we add a hidden layer HT to have a feedback loop in our process. So, for example, if we first put the "is a bad movie" to the model, so we will have H1 to H5. So we save the information of the first sentence. So for the second time, if we put "is not a bad movie," so it will know that we have some relationship to the "is a bad movie." Yep. And this
that's for the example that we discussed before, right? So you guys both like the word bad, right? So it's it's good.
Okay, so here's the actual model we define. So we use 32 neurons in the simple RNN. Yep. So here's the result. So for the full test and the long test, there's no big difference. So it's around 80 accuracy. But for the short test, it's only around 57 to 60%. And if we increase the training data put in the model, so the short test will increase to around 70. But there's no big change in full test and long test. And here we still use the 10K total training data. Okay.
So, and here, do you do padding, or do you do padding here or not? You still do
Post-padding.
post-padding.
Yeah. We will discuss the padding strategy later.
Yeah, because here you see that you are not learning for the short one on the RNN. And then as you use more training data, then the accuracy decreases. So when you give me, so just a second, let me process, right? So validation accuracy gets to 77. So it's still increasing though, right? So the model is still learning for the RNN with 25,000 data, right?
Yeah.
Is that correct?
Yeah.
You see that after 5 epochs, it's still increasing, right? It's not. Go ahead.
Because we only used 5 epochs here, so we think there's no overfitting, and we also print out the valid accuracy and the value loss, validation loss, and yeah, but there's too much graph, so cannot show in this
Yeah,
page.
because the model is overfitting, but it's still somewhat learning, right? Interesting.
Yeah.
And this is the test model, and I have built another test model here, and it got better results, which we can get the short test from 10,000 data to almost 80% accuracy, and long test data from 10,000 data to over 90 accuracy. And this
how do you
model.
change it? Go ahead.
Okay.
可以帮我回去前两。
Okay.
Tell me
this
how
part.
it is. Yeah.
So the upper one is we use for the test, which gets bad results, and the down one is I change a little bit to get better results. So we just turn the mask 0 on to make sure that the padding doesn't affect the model too much, since we use 500 lengths both on short and long. So if the short is too many padding, it will affect the model too much. So I turn the mask 0 on. And also,
you're just removing the
and
mask.
also the bidirectional, which gets the data from the previous to the end, and then from the end to the previous, and which make the RNN model to learn better. And the dense layer is still the same. So I use the down model to train, and which gets the better result and not overfitting that much.
Yeah, good.
Okay, next is for the GRU model. So for the variation of the RNN, he add different gate, such as the update gate and the reset gate. So it will it solves the problem of the vanishing gradient in RNN and make the model become more stable and better reserve the memory. Yeah. So here's the actual model of GRU. So which is similar to RNN, still using 32 neurons. And here is the best model, another better model for GRU. So similar things. Yeah.
So what is the
reset?
implementation? Yeah. Tell me. Yeah, tell me about the hyperparameter.
The reset after and that implementation, just to tell the model not use cuDNN for the training, because TensorFlow kind of can use GRU model on cuDNN training environment. So that just tell the model to use the original TensorFlow GPU to train.
Thank you.
And and other thing is just like the RNN, we turn the mask 0 on and bidirectional to the GRU model. Yeah.
Okay, so here is the result of GRU. So compared to RNN, the accuracy become higher. So the full test and long test in 10K train data has around 90% of accuracy. But the short test has only around 80 accuracy. So it will become high accuracy if using more training data.
So here you have the mask on, right? So the padding doesn't play a role anymore, right? Correct? Yeah.
Okay.
No, it's a question. Yeah. Let me look at this a second. Right? Then you have the mask on, so you recognize the mask, right? So you don't run to the mask of all zeros, right?
This part is the test model, which doesn't have the mask on. So in this part, it still matter.
Okay, good. Okay. Just a second, guys. So the short reviews, a little bit of stay there, please. Let me take a look. Okay, so there is overfitting, right? There is still overfitting, but the learning is taking place. And what you do is that, so the GRU long reviews You're stuck at 80 something. Tell me this, the last row, second image, what does it correspond to?
Overfitting, maybe.
Second image.
You
Last
mean-
row,
Yeah, last
second
row.
column. Last row, second column.
Here.
Yes.
Oh, that's very
So which scenario is that one? So that's the long review. That's the GRUs.
The
yeah.
right side is the test accuracy, and the left side, the green bar, is F1 score.
So, but how many? This is for 25,000 data point.
No,
Which setting is
10,000.
this? 10,000.
10,000.
Okay, go ahead, guys. Yeah.
So here's the model of another model. Yeah.
Here
So
we
it will
turn the
have
mask on and use bidirectional.
And then you see the jump to 92, right? Very good.
Yeah. Yeah. Okay. Now's the time
So
for another
here-
debate. 你要开吗？还是
So here is the padding strategy we talk about in the section 6. So here we use different position padding, which is pre-padding and post-padding and center padding. And here is how we implement the center padding. We just see how long the original sequence is and divide it into the front part and the last part and put the padding inside the front part and last part. And the pre-padding and post-padding, we just use the original function the pad sequence provide. Okay, so here is our CNN model training on short and long data set with different padding strategy, the results of all the accuracy. So we can see that the post-padding do the best job here in the CNN model, but almost the same since the CNN doesn't care when does he get the message. Okay, so here is the graph for long data. Next page. And here is the result of Arnold model, which we can see that its accuracy is pretty bad in pre-padding, and which it gets better at post-padding since Arnold sees the closest data are more important than the previous data. So the result is kind of make it sense of that. And then we can see the photos of short ones down there. And next page. And here is the long data's plot. Next page. And this is GRU's performance. We can still see that the post-padding here is not the best case here. Almost 3 are average since the GRU will see which token is most meaningful and catch that point. So it doesn't matter where we pad the paddings, and it got almost the same accuracy.
Correct.
Okay, so here's the overall accuracy in this section. And we can see that the post padding to the RNN is the best, and to the CNN and to the GRU is almost the same.
Good.
Okay, so this is another part of our padding strategy. We use different values, 0 and 1, and randomize. So here is how we implement our code. So the 0 and 1 padding strategy, we use the original pad sequence value, just changing the value to 0 or 1. And the apply random padding, we use the random generate 0 or 1 and add it back to the original sequence. So here is 3 different padding strategies with different values. Next page. And here's the result of our CNN model. We can see that it still doesn't affect it much since the CNN is just watching overall thing. So yeah, the
you're max
accuracy is
pooling, right?
best.
So max pooling takes everything, right? So
yeah.
Very good.
And the next page is the long data with CNN training. Okay, next page. And here is the RNN result. Here it performs slightly better with the padding 0 in the long data set, and with the 1 and random padding, it gets terrible outcomes. But still, we find that 0 padding is the best for RNN model. Next page. And here is the long data set for RNN graph. Next page. And this is GRU. So with GRU, the 1 and random padding will make it worse, since the GRU do take care of the word's meaning. And since the 0 padding will tell the GRU model more correct that that is just not needed information. So here the GRU performs best under the circumstance of 0 padding. Okay, next page. Next page. And here's the overall result.
Yeah. Makes sense, yeah.
Next page.
Yeah, so there is just this thing that please redo this with the smaller network for the shorter one, if you can, for the CNN, so that it's more to the point. The rest is perfect. Yeah, guys, the rest is really good.
Okay.
Go ahead.
So here is the advanced padding techniques with noise padding and reflective padding. So the noise padding, we just randomly generate the number and put it inside the sequence, and use post padding. And the reflect padding, we just copy the original sequence and flip it, and then add it to this, and then do it until it meet the max length. Next page. And here is the result. We can see that, yeah, the CNN is still the same. It just performs very good at every kind of padding. Next page. Next page. And here, the RNN model, we can see that with noise padding, the short one do the best, but it is kind of weird. So I think it's just because it overfeeds with the short data, since not enough data, so the accuracy is not that really accurate. And the long data, we can see that Plan 0 does the best, and that is what we want to see. But the noise is still doing very good. And yeah, that's a very cool thing that we discussed. The noise padding will make the RNN model have the better accuracy. And next page. Yeah, next page. And here is the GRU models. With GRU models, the 3 padding strategies all make it do good, except the reflective short padding. Since the GRU will catch the important token, and reflecting makes more important token, and which will make it misunderstanding the sentence, so its accuracy is dropped slightly. So yeah, that makes sense, and that's what we get from the GRU model. Yeah, next page. And this is the overall accuracy. And thank you, it's our project.
Very nice. Nice. Thank you, guys. Thank you, guys. Yeah, good job. Good job. Good job. Good job. Okay. Yeah, I was trying to remember because I think at the idea of the random padding, I just came up with the idea just to make the challenge more interesting. But then I figured out that it actually does work. So I think it's not a common thing to do. I just rammed it up to keep you guys busy. Yeah. Okay, very good. I suggest we do like a quick presentation from the usual Harvard data set, the Harvard lectures, and then I think we move on. So let me just discuss a little bit what's going to happen next. So next challenge is you guys choose your teammate as you want. Huawei will release the sort of a summary of the performance of the different students with the role that they chose, the average inter challenge review, and the average intra challenge review, and then the number of 0 that they got, right? So I told you that if somebody doesn't participate, just give them a 0, and then we can see from the 0 who is not participating and so on. And yeah, I saw that in Slack there are a few people that They are describing the difficulties that they have. So we do expect to have a drop of people after the midterm week. That's usually what happens. People just drop the class and they don't tell anybody. So we're going to reduce the number of groups, probably of one. So we're just going to have a group moving on. But that's no problem. But then, of course, yeah, you can choose the team members as you want. And yeah, if you have any other question regarding this, let me know. Otherwise, we go to the next presentation. As I said, yeah, I hope you guys sort of understand what we're trying to do, right? The class organization, it's focused on group one member want to report. So there was one member of group one that didn't participate. Is that what you mean?
Yes, Professor.
Yeah, just give me a 0 or yeah, just give me a 0 and then we'll see the zeros in the review, right? Is that what you meant? Yeah. Go ahead.
Because we have one RNN model didn't presentation, so we wanted to presentation now. Or maybe you maybe
okay, go ahead.
Oh, okay.
No, go ahead. Do it now.
Oh, okay. Thank you, Professor.
Group
may
one.
I
Yeah, because the
share
RNN was missing, right? So you guys did it.
Yeah. It's me. Sorry. May I share my screen now?
Where did you go? Huh?
Okay.
Were you busy with something? Did you go to the doctor? What happened? Are you okay?
Okay.
He has an expensive keyboard, guys. Can you hear his keyboard? How the noise that it makes? It's one of those expensive clicky keyboards. Must have.
Professor, do you see the screen? The coding.
Yeah. Of course. Go ahead.
Oh, okay. I'm shortly to introduce my RNN model coding, and this part is as you can see, it is doing the data loading, reloading the IMDb model from the TensorFlow. IMDb, yeah.
Go ahead.
From the TensorFlow, and in this part, we are doing the post padding processing. You can see the tokenized the review tokenized. You can see it reviewing the CO in the bed, and this part is for is doing the prepadding the data the prepadding, and this part is for the center padding. So we're going to the RNN model. So this is my RNN model. It is the single layer and the dropout. I choose the simple RNN with the one layer because I want to prevent the vanishing gradient. Because I'm trying to add more layer, but I discovered that the model will overfitting and it can't convergence. So this is the performance for the post padding data. The short comment post padding performance, and this is for the long comment. The performance of long comment.
and this is the graph for the short review and the long review. This all is post padding. As you can see it, wait a minute. As you can see that all the training is going to convergent, but in the approach 4, but after that the loss will increasing. So I added the code for early stop when the loss increase, the training will stop it. So so it's perfectly to do this. Okay, and the next part is for training the pre-padding data. We use the same model, just the simple IN with one layer. This is the pre-padding performance for the short review, and the next part is for the long review pre-padding. This is the graph. As it have the same problem in the post padding. When we going through to the free approach, the loss will increase dramatically. So I adding the same code for the early stop. Yeah, and the next part is this is the center padded. This is the performance, but in this performance, we discovered that, and this is the comparison for the free padding. As you can see that post padding and pre padding has have the good performance in this challenge, but central padded, as you can see, especially in the short review, we have the lowest accuracy. This is
it doesn't learn, right?
Comparison for the loss. Yes. As you can see that in the short review, the center padded is has lowest performance. So this is this is our RNN model for and we doing the free padded, pre padded, center padding and the post padding. When I think in that after this presentation, I will do another padding, such as the random padding and other technique. So, my presentation is finished.
Yes, so there are no padding should happen. Okay, very good. Just don't leave, okay? Don't leave. Stay with us, okay?
Oh, okay.
Okay, so let's do a little bit of slides from the course, and then we'll move on with our lives. Yeah, if you can stop sharing, please.
Oh, okay.
Right.
Thank you, Professor.
You're still sharing. You're welcome. Next time, try to be on time, right? So that easier for us. Okay, just 10 minutes. No problem. Just 10-15 minutes, right, of slides, guys. So as I was saying, yes, so from now on, you can have your group. So the suggestion is to start thinking now about the final project. As I said, I'm hosting this competition, so if you want to participate there, I'm just happy because I already know how the challenge should go, so it's easier for me. Also, you can win some money, and you can share the money with me if you want. Otherwise, yeah, so as we said, so we expect some people to drop from the class after midterm week. So some people realize that they need to focus on some other classes that are mandatory. And of course, they don't tell us anything, that they stop coming to class. So just bear in mind, right? As I said, I hope you appreciate our efforts in organizing the class in the way it's organized. And of course, we have little control over the people that decide to stop contributing to class. And it's unfortunately, as we discussed, right, there are many reasons for this to happen. And let's say that we try to do our best despite this limitation. Okay, just very quickly. So just a very brief introduction to NLP, since I just want to give you some high level, right? So very surprisingly, right, NLP has become the most important application of machine learning in the last 2-3 years, right? So now, NLP has sort of jumped to the forefront of AI applications, right? And the idea is that as humans, we have generated a lot of NLP data, right? So here, just some statistics for you, right? So of course, there is a lot of written data, and there are many levels of NLP, right? So here there are some tasks. So for example, the easiest tasks are the syntax, right? So for example, you want to do word segmentation, part of speech, parsing, right? So these are sort of the morphological properties of language, right? Again, English language is very different from Chinese, but you understand adverb, adjectives, gender, number, this type of stuff. Then there are a little more high-level performance, which is summarization, for example. So somebody gives you an article and you have to produce as a task, you have that of summarizing the article, and then much more semantic problem, right? So for example, sentiment analysis is the one that you did today. You have to decide whether a text is positive or negative. Language understanding, machine translation, right? Question answering, language modeling. These are more the domain in which LLMs are nowadays having the best performance. So, for example, somebody gives you a bunch of articles, and then as a summarization task, you want to say if the vaccine is safe or non-safe. And for example, topic modeling, right? Somebody gives you a bunch of documents. You have to decide how many articles have to do with sport, how many with news, how many with fashion, and so on and so forth. And then natural language understanding is, for example, this example here, right? So somebody's talking with the Alexa device, and they don't support anymore, but let's assume that we still have the Amazon Alexa. And they have Play, driver license by Olivia Rodrigo. That's also like a very dated reference right now. But of course, the intent was to play a song from a certain artist, right? So that's it. Machine translation, you understand it, right? When you go from one language to another, El perro marrón, the browning dog. And so this is a little bit this. So let's discuss about language models. Okay, so the language model is a representation of the language used by a given entity. Okay, so a particular person, a general, another well-defined class of text. Okay, a language model represents the language used by a given entity. So, for example, you want to distinguish spam versus non-spam, right? So a person that is writing a spam email will use different language from a legitimate email sender. And also different languages, right? So if I have documents of different languages, this corresponds to different language models, okay? So we can also look at the language model as a formal definition. And this is where we get to this type of probabilistic description of the language, right? So let's say that we have the set of all possible words that a person can utter, right? Then we can have a probabilistic description of a certain sentence as the probability that the sentence appears in the text. Okay, so we can say that Anki was late for class. This is a composition of 5 words, and we can ask ourselves what is the probability that this sentence occurs in the language in general, right? And this is a little bit what you see when you do Google, right? When you look something in Google, as you complete more and more words in your Google query, then you will see that Google will use a predictive model to try to predict what type of sentence you are trying to write. And this is, of course, just a probabilistic model, right? Meaning that they saw a bunch of queries, and from this bunch of queries, they're trying to predict what is the probability of the next word given the past word. So this is sort of a conditional distribution description of language. Of course, now we also have personalization and many more complicated models, but at the first approximation, you can think of this as a predictive, like as a probabilistic description of language. Another example are predictive keyboards, right? Again, let's take out personalization and more complicated algorithms. You can imagine that as you produce a text, right, the probability of the next word given the past word, or it's a probability that you can describe efficiently. Okay, this is again language modeling. And then why do we want to have a language model? So there are 2 main tasks, right? One is generation of text. So these are, let's say, some generative models, right? So if you have a probabilistic description of the language, you can initiate a sentence using a random seed, and then the language model will be able to generate a full sentence from this random seed. Or, of course, and also classification, right? That's what you were doing, sentiment classification, auto-shape classification, detection of spam versus no spam. These are all tasks that we can do. And, of course, many more downstream tasks. So what is the scenario under which the language model occurs? So we assume that we have a finite vocabulary V. This is also something that you experiment with in the challenge for this week. So we don't allow for an infinite bag of words. We don't allow for the generation of new words. This is understandable. And we are given a training set of sentences from this set. And the problem is to estimate the probability distribution of a certain subset of words. Okay? So you see that, for example, if you look at the probability of a single word, for example, we said that there is the most common English word in, say, the set of all possible English utterances. And then we see that the sun, okay, this sentence has a much lower probability than the, because we have a longer sequence of sentences, and the probability that okay follows sun is very low. So the probability of this, let's say, utterance is 2 to the minus 13. And also, if we get the longer sequences that contains more nonsense, for example, waterfall the ice cream, then the probability keeps dropping because the probability of this sequence of words is very, very unlikely. Okay. And why do we do this? Because sometimes we are trying, for example, we are trying to understand a certain sentence. So let's say that we are doing a speech-to-text model, and we're trying to answer queries from a users on a mobile phone. Of course, if somebody asks what is the weather today, then you know what is the weather. Of course, this is in Cambridge, Massachusetts, because it's on Harvard. And you can see that you can misunderstand the sentence as today or today or today. Or weather can become a personal name of weather. So it's clear that all these sentences, right, they are very unlikely. So it's clear that if we have a probabilistic model and we are uncertain in our text-to-speech model, what is the weather today is a much more likely sentence than all the other 3 sentences. And so we'll be able to answer the query with confidence, even if our text-to-speech model made a mistake, because we understand that the probability of a certain sentence is much larger than the other. Okay, so now we want to have this type of machinery, right, that produces probability values for certain utterances, right? So somebody gives us a string of words that come from a vocabulary, and we want to produce a probability for this. Okay. Of course, we can start thinking in terms of n-grams, okay? So what is an n-gram? For example, we are given a token, right? And a token is an occurrence of a word in a text. A word type refers to a general form of a word defined by its lexical representation. So you don't want to say run, runs, you want to have the same type of word for the different declination of the words. So if the corpus were just I run and run and run, then you would say 6 word tokens, which is I run and run and run, but you only have 3 types, which is I run and, because run is repeated and n is repeated, okay? And if it was runs or run RUN, then it would be the same. And then we can say, well, the probability of a sequence of word from omega 1 to omega t is equal to the product of the probability of each word. Okay, so this is a unigram model, meaning that we model each gram, each word, as if it were independent. Of course, this is nonsense, right? Because we remove the sequential dependency of the word, but it's the first model that we can have. And of course, in order to describe unigrams, the only thing that we need is the probability of the word in the dictionary, right? What is the frequency of the word in the dictionary? Of course, this is not very useful, but it's just there to introduce us to just a second, I want to go to this. To introduce us to bigrams. Okay, so what is bigrams? Now, instead of considering 1 word at a time, we consider 2 words at a time. So we said that the probability of a word is the probability of the word given the previous word, right? So the probability of a sentence is equal to the product of these conditional probabilities. Okay, so you guys must have done conditional probabilities by now in your life. So you know that if we assume that the current word is only depending on the previous word, then we can write the probability of the sentence as the probability of the conditional distribution of all of the words, of the pairs of words, right? The conditional probability of the current word given the past word. And in order to estimate these probabilities, we need to estimate the probability of the word omega 1 prime given the word omega. And the way to obtain this is by taking the probability, the number of pairs of words omega and omega prime, and divide by the number n omega comma omega star, which is the number of times that the word omega appears of a first token in a diagram D. Okay, so this is how we estimate this probability of the next word given the previous word. And of course, once you understand how you go from the unigram model to the bigram model, then you can extend this to any n-gram model, okay? So what we're doing is that we're always calculating the probability of the current word given a certain windows in the past, and the length of the window is what controls sort of the complexity of our statistical model. Okay, so what are some of the issues? So remember that here we are explicitly modeling probabilities. So there is a probability that you have an out of vocabulary bigrams, right? So there is a sequence of words that never occurred. And so for this sequence of words, you have to decide what to do, right? So if you have a bigram that you never observed, what will be the you never observed in your data set, you have to decide what is the probability of this to occur. So you sort of have to, you cannot leave it to 0, of course, never leave anything to 0 in probability estimation, otherwise very bad things will happen. So you have to decide, let's say, a certain baseline probability that you say that any sort of bigram has a probability of occurring of 10 to the minus 13, right? Something like that. Then notice that in the unigram, we have to store the probability of each single sentence, each single word in the dictionary. So if our dictionary had size L, right, then we needed to store L different probabilities. Now we are storing pairs of words, right? The probability of a word given the previous word. So now the storage space will become twice as much. So L square, not twice as much, will become the square, right? So L square. So you can imagine that this scaling will continue, right? So if we have a 3 gram or a 4 gram, so if we look at the current word given the past K words, then the complexity of storing this probability distribution in our computer will be L to the power of K plus 1. And remember, another issue that we have is that there is no semantic understanding, right? So we just look at the dictionary and we just assume that any possible combination word happens, and we estimate this possible combination. So there is no semantic closeness between the words. And for example, here, vehicle and car, we understand that they are semantically correlated. So the bigram of one should relate to the bigram of the other, so on and so forth. Okay? Good. So in order to avoid stuff that doesn't occur, we can have a normalization. And usually what you do is that you have the count plus in alpha divided by the marginal count plus alpha times the size of the dictionary. And this usually prevents like some numerical instabilities in the managing of the bigrams, okay? Because since you're taking the product of many of these probabilities, you can imagine that this operation is numerically unstable. And what we have is that we still have the out of vocabulary bigrams. So, of course, when the word COVID-19 emerged, this didn't exist before. And then we had a bunch of new medications. So also in the case, we didn't have word for this. So we don't have a way of accounting for the emergence of word in the language. And what you can do is that you can have some sort of smoothing, right? You can say that if you observe a new word for which you don't have a probability, you can, again, do some smoothing operation by adding some constants and dividing by some number which is far away from zero. So now we have this smoothing constant alpha and beta, one for the bigrams that don't occur, and the other one is for bigrams that correspond to new words. And this becomes a problem of fixing hyperparameters, right? So we have to sort of estimate what is the probability that of the emergence of unseen bigrams and the emergence of new words in the data set. So, sorry, the emergence in new words in the language. So this is something that you understand, okay? And this is where, for example, the unknown token comes in, right? So we associate all the unknown words to this unknown token that you also see in the challenge for this week. And so this is the role of the unknown token. We want to avoid the data set to have to account for all possible combination of words of a certain length. So we just use the unknown token. Okay, very good. So remember, you also saw that you have some other tokens. So for example, there is this padding token, right? So if you want to, let's say, distinguish a sentence from another sentence, you will have the S token as sort of a service token to distinguish different sentences. And you do this because usually you want to drop the notation, right? So if you have a sentence which is I ate, okay, did you eat? Of course, these are two different sentences, but we don't want to carry around, let's say, in our dictionary, we don't want to distinguish between punctuation, between uppercase and lowercase letters. So we just use the marker S to demark different sentences. So you have S, start of the sentence, I ate, end of the sentence, which is also a start of the new one. And then you have the next sentence coming up. And why do we want to have these engrams? We said that generation is one of the tasks that we are concerned with. So the idea is that we could take an initial token S, right? And then we just generate a sentence by sampling, right, for the probability distribution of the next token given the past, right? And this will produce a certain set of, let's say, tokens. And then eventually we're going to end up to a token in which the token that we sample is a token plus end of the sentence token. And this is how we will terminate the sentence, right? So in this random generation mechanism, there is also an internal mechanism that says the sentence starts here and the sentence ends there, and the length of the sentence is also random, okay? Just a second. So of course, once you understand the bigrams, then you can understand engrams. So the idea is that we look at the current word given the n past words. Again, the Bayes theorem and the conditional probability still holds. So we can still describe this as a product of probability distributions. And then, yeah, so this is how the generation extend beyond the 2, and you understand what are all these issues, right? So the issues that we encounter are the one before. So we have the idea that the probability of any specific sequence decreases with the size of the window that we look at, right? And then we having to deal with probability distribution is it's very tough because you're dealing with multiplication of numbers that are tending to 0 as the length of the sequence increases, because the probability of the sentence now it's the product of a term with decreasing probability, and so you have to move to the log domain so that the multiplication, so that this Bayes rule now becomes the sum of the log probability. So now you move to the log domain. If you take any probability is between the number 0 and the number 1. So if you take the log probability, then this will become a number between minus infinity and 0. So if you take minus the log, then you have represented the probability between 0 and plus infinity. And then we come to this concept of perplexity, right? So this is a concept related to entropy, and measure the uncertainty of a model for a particular data set. Okay, so if you have a very high perplexity, this corresponds to a lot of uncertainty on your generation. And the perplexity is measured as the number of the average number of bits that you need to represent a word, and you can see this as a branching factor. Okay, so as the end of the model grows, then you are adding more condition into your word representation, and so you have to select all the possible words out of this. And if you measure the perplexity of good models, it tends to be, let's say, around 40, 100 to a large corpora. And if you assume that the use of the words is uniform, then the perplexity will correspond to the unique word types in the corpora. Very good. We don't need to spend too much time on this. And this is the evaluation of perplexity of a unigrams, bigrams, and trigrams. So you see how the perplexity drops very quickly from unigram to bigrams, but then bigrams to trigrams, they still decrease, but not so drastic. And of course, the complexity of this model goes from L to L squared to L cube. So you pay a lot of complexity in decreasing the perplexity. And yeah, let's just stop here for now because we had a long day today. So just a brief introduction on language model. What do we use language model for? Classification or generation, for example. And we saw how we can generate language probabilistically. Then we gave a measure of performance of the language model in terms of complexity. And then we discussed the trade-off between complexity and precision when we use unigrams, bigrams, trigrams, and n-grams in general. Okay, very good, guys. So as I said, I don't want to do too much frontal teaching. I think it's good for you guys. So this Friday we release the next challenge. Remember that now you can choose your team members as you want. So as soon as we release the challenge, make sure that you find some teammates that you like. And as usual, I'll be here online for a few more minutes. If you have any questions, let me know. Otherwise, I'll send you this set of slides and then we'll discuss later. Okay, guys? We also stop the recording, so go back to our future selves. Eh?